Have you ever rolled any dice or tossed some coins and wondered what the chances are that a particular side would come up? You were intrinsically wondering about the probability, or quite simply the possibility, that an event will occur with respect to a certain frequency with which the event is likely to occur. Concepts of probability can be applied to Mendelian inheritance using something known as the multiplication rule. Before we get to this, let's have a very brief review of concepts related to probability. Any event that is certain to occur has a probability of 1, and the event that is certain to not occur has a probability of 0. For instance, let's say you have a coin that has tails on both sides. The probability that it will land on tails after you flip it is 1. Of course, in a normal coin, that probability is only 1/2. The sum of all the probabilities for all the possible outcomes have to add up to 1. In this example, we have two outcomes, heads or tails. Each outcome has a probability of 1/2. Therefore, 1/2 plus 1/2 is equal to 1. What you probably realize intrinsically is that each flip of the coin is independent of the prior flip. You know that the outcome of the current flip is not influenced by the outcome of the prior flip, nor would the outcome of the flip of one coin be influenced by the outcome of the flip of another coin if they're flipped simultaneously. This means each coin toss is an independent event because the outcome of any toss is unaffected by the outcome of any prior toss or the simultaneous toss of another coin. This is important to note because according to Mendel's second law, the law of independent assortment, the alleles of one gene segregate into gametes independently of the alleles of another gene. Confused? Well, if you were to flip a penny and get heads, will that influence if you get heads or tails when you flip a nickel after that? Of course not. Same thing here, except we're dealing with a pair of alleles of a gene instead of a pair of sides of a coin. Now, what are the chances that two or more independent events will occur together in a specific fashion? Meaning, if we were to flip the penny and nickel at the same time, what are the chances that, say, both simultaneously land on heads? In order to figure this out, we need to use the multiplication rule, the multiplication of the probability of one event by the probability of the other event. What's the probability of the penny landing on heads? 1/2. What's the probability of the nickel landing on heads? 1/2. So, 1/2 times 1/2 is equal to 1/4. Using this, we can turn to something like the F1 monohybrid cross, where F1 refers to the first filial generation, the hybrid offspring of the P or parental generation. When the F1 hybrids self-pollinate or cross-pollinate with other F1 hybrids, they produce the F2 generation, the second filial generation. Let's just say that the shape of seeds in the pea plant is our heritable characteristic, and the genotype of the F1 plant is big A, little a. This means an egg has a 1/2 chance of having the dominant allele big A, and a 1/2 chance of having the recessive allele little a. The same thing goes for any sperm cell. This means that if an F2 plant were to have a recessive trait, little a, like wrinkled seeds, then both the sperm and egg must have the little a allele. Based on everything you've learned thus far, what then is the probability that a little a allele will be found in both gametes, the sperm and egg, during fertilization? We know the probability of little a is 1/2. This means all we have to do is multiply 1/2, the probability the sperm will have little a, by 1/2, the probability the egg will have a little a as well. That equals to 1/4. Thus, the probability that an F2 plant will have wrinkled seeds is 1/4. You now know how to apply rules of probability to Mendelian inheritance. Probability is simply the possibility that an event will occur. Any event that is certain to occur has a probability of 1. Any event that is certain to not occur has a probability of 0. The sum of all the probabilities for all the possible outcomes have to add up to 1. We can apply the multiplication rule to Mendel's second law. The multiplication rule is the multiplication of the probability of one event by the probability of the other event. Mendel's second law, the law of independent assortment, states that the alleles of one gene segregate into gametes independently of the alleles of another gene. Using the example in this lesson, you should now know how to solve similar problems on your own.